Hello students, in this video we will work the first set of problems from chapter 2. And the first problem is actually somewhat familiar. I've drawn a little diagram here of what's happening. It says that a person who's climbing on a cliff is rescued by a helicopter and that the person weighs 50 kilograms. I guess it looks more like 500 kilograms in this context, but the person weighs 50 kilograms and is accelerated upward by the helicopter at an acceleration of 5 meters per second squared, and this problem is asking for the tension. And this is something where we've done similar things repeatedly. So you're going to have, what you're going to have is a tension force. So if I drew the free body diagram, the way it would look is I'd have a force at mg, or m in this case is 50 kilograms downward, and then I'd have an upward force. This is the tension, and the tension has to not only cancel the mg, it has to also provide an additional acceleration of 5 meters per second squared upward. So, I mean, one easy way to think through this would be that you need two parts to cancel the downward force of gravity, mg. You need the same amount of force upward, which would be 50 kilograms, I won't put in the units here, times 10 meters per second squared. And so this is 500. And then to provide additional acceleration to go up at 5 meters per second squared, which is half the acceleration due to gravity, or about half. So to accelerate up at 5 meters per second squared, you need an additional ma. So this is in Newton's second law, mass times acceleration, which would be 250, and so these will add up to 750, and that will be answer choice C. Okay. Now number 26 asks for the net force on a skydiver at terminal velocity. This is another thing we've already talked about. So terminal velocity means when you jump out of the plane, at first you're accelerating downward due to gravity, but the faster you go, the more wind resistance you're experiencing because the air is pushing against you faster. And so terminal velocity is the point at which the wind resistance exactly balances the force due to gravity. Now this idea of exactly balancing, so this is terminal velocity. So it means wind resistance balances downward force due to gravity. Now this word balances, that indicates the forces are the same, and so the net force will be 0. So you have, if you draw the picture, you have, here's your little parachuter, and so you've got two forces. You've got mg, and then you've got wind resistance, which I could call the force due to friction, because it's one of those types of friction drag, and they cancel. Now it doesn't mean he's not moving, it just means he's not accelerating. He's moving downward at a constant rate, and that's the terminal velocity. But the net force is 0. So when you write F equals ma, remember this means net force. Terminal velocity not changing, that means A equals 0. So the force will have to be equal to 0 as well. That's another way to think about it. And that's the answer choice A. Okay, number 27 This is not too difficult of a problem. It says that there are two forces, well, there's actually a total of three forces, but it begins by telling you that two equal forces are applied to some object, one force pointing east and the other force pointing north. And it says that you want to cancel out the effect of these forces by adding in another force, and it asks you what direction should that force point. I think it's pretty self-evident. See, this is one of the ones where, you remember I told you with the 5-step solution method? You can solve this. Can't you tell immediately that it's going to be southwest direction? I mean, you can just eyeball that and answer it immediately. You don't have to think about, what's my 5 steps? What step am I on? All this kind of thing. So these two forces, you've got one pulling north, one pulling east, and you have to pull southwest in order to cancel these out. You know, you could think about a person, like there's a rope attached here, and there's a person pulling this way, there's a person pulling this way, they're pulling the same amount. What way do you have to pull in order to keep them from moving forward? Well, it's going to be this way. It's exactly balanced. It's along this line. It's a symmetrical thing, because that angle is going to be the same as what that angle is there. So that's pretty self-evident. I mean, you could break it into components and write a bunch of equations and do all this kind of thing. I think that for 95% of you, it's better to just say, hey, I know it's southwest. Now, I forget which answer choice that was. Let me see if I can, yeah, so that's answer choice D. I forgot to write that on here. Answer choice D. Okay, so, and I forgot to write the 27 here. Sorry about that. I always seem to do that. 28. So this one asks you which of the following systems are experiencing no net force. And it has 4 systems here. So the first one, you have a car, and it starts out at 0 and it accelerates. So it's going up to 80 kilometers per hour, I think it was. 0. Or maybe it wouldn't be meters per second, so that'd be really fast. I guess it could be. It doesn't matter. It's not going to matter what the numbers are, but we'll just say it goes from 0 to 80. Well, it has to experience a net force or else it wouldn't accelerate. You know, it starts out at 0, it gets to 80, so that's going to be an X. That one certainly does experience a net force. Now, the next one says you have a bucket that's lowered at a constant velocity. So you have, you know, so you're lowering, you know, say you have like a pulley here and you have this rope that goes over here, and then you have, here's a bucket, and it's being lowered at a constant rate of 2 meters per second. Now you might think, well, it's moving. Surely there is a net force on it. But it's moving at a constant rate. See, in all these cases, you should be thinking back to F equals m times A. And that, remember that this is net force. There's no acceleration here. It's being lowered at a constant velocity, so that means 0 acceleration. And just like in the other problem, this is 0, so that's 0, and 0 means no net force. So that one does experience no net force. Now the next one says that you have a skater on ice, and so I can't draw a skater, but let's try. I don't know, is this like gender stereotypical to draw it as a girl? I guess it could be either way, right? I can't draw ice skates. Anyway, she slows down. So she gradually slides to, or glides to a stop or something. Well, you think of ice as something that doesn't have much friction. That's why you can skate on it, or you slip on the ice. Not down here. I mean, there never is ice, but if you lived up north, in the winter you'd slip on ice all the time. So it has little friction, but it has some. It does have some friction. And so this whole time that she's gliding along, there is a force due to friction pushing back, or else she wouldn't stop. If there was no friction, then she wouldn't stop. She'd just keep on gliding at the same rate. So there is a net force. That's that force due to friction. And so this is not an example of no net force. And then the final example is a pendulum. And so you have this pendulum that swings back and forth. Say it hangs from I don't know, whatever it hangs from. And then you have the ball of the pendulum here, and it swings back and forth. Does it experience a net force? Yes, because it keeps changing direction. It's not moving at constant velocity. It accelerates this way, stops, accelerates back this way, accelerates this way, and so on. So that's an X. And it turns out, I forgot to write it again. Let me look and see. Yes, they agree with me, fortunately. The answer choice here is B. That's the bucket being lowered at a constant velocity. Okay, so let's move on to 29. What this one says is that I have a utility pole, like a telephone pole or something, and it has some lines attached to it, and they have tension in them. And in particular, let me draw that a little bit shorter. In particular, you have a line that's up a distance of 4 meters. And it has a tension of 200 newtons in it, so it's pulling that way. And then you have one that's a little bit lower down here. This is at a height of 3 meters, and it has a tension of 400 newtons. And what they ask you is, what is the net torque on the pole? And this is kind of a trick question. And it's maybe not quite fair, because they don't really tell you. They kind of imply, they say the pole stands there, but they don't really guarantee to you that the pole's not moving. So you're supposed to assume that the pole doesn't move. And in that case, so the net torque must be 0. Now you could argue, oh wait, no, it's not, because see, here, you say you take this as your fulcrum, and you could say, well, there's there's a lever arm of 4 meters, 200 newtons that way. The torque, I'm getting a torque here, 800. Here, 400 newtons, 3 meter, I'm getting a torque of 1200. What's happening? Well, what you're supposed to think about is the fact that this is also connected to the ground, and the ground can exert a torque on here. So this one is, I think it would be understandable if you didn't answer it the right way. It's kind of a trick question. So this is sort of a trick. So, and what the trick in it is, don't forget the ground. See, there can be a force that's exerted on this thing by the ground as well, and that will have, if the thing's not moving, then that's going to have to cancel out whatever is happening with these two here. So that came out to answer choice A. Now, of course, if you didn't know that, on this one, if you didn't know that it's supposed to be stationary, then you'd get a different answer. It would fall that way, because this torque would be greater. But you're supposed to assume that the total torque is going to be 0 because you're supposed to assume that it's not rotating. Now, number 30 draws pictures of wrenches, which I've simplified to these free body diagrams where the wrench, instead of drawing the wrench, and so here you have like a bolt. Those bolts are like hexagonal maybe or something. Let's see if I draw a hexagonal bolt here, and then I have a wrench. So here's my wrench, and here's the handle of the wrench. And so in each case, these little line segments here represent the handle of the wrench, and then you have these forces. So the first one has the force going pretty much perpendicular out that way, and then the other ones have the forces at different angles. And you're supposed to assume that these forces are all the same. So I could draw an F here, an F, an F, and an F. And they're the same size each time. And so the question is, you have the same sizes of forces, which gives you the most torque? And it turns out it's this first one, answer choice A. Why is that true? Well, in particular, why isn't it this one here? Well, because the sine of the angle is smaller. The angle's not 90 degrees. Here the angle's close to 90 degrees. So here the sine of the angle is smaller, and that makes the torque less. You remember our torque formula. It's the size of the force times the length of the lever arm times the sine of the angle between them. So here it's because the angle is bad. And you know from experience that you want to, when you're trying to like use a ratchet or something, you want to, or a wrench, you want to push perpendicular to the lever arm. Now here it's perpendicular, close to being perpendicular to the lever arm, but it's too close to the fulcrum, so the lever arm isn't as long. So in this case you have small theta, and so that makes this be small. In this case here you have small r, and so that makes the torque be small. Here you have large theta and large r. Now this one won't work once again because of the angle. So in this case you have an obtuse angle, and it's bigger than 90 degrees, and the sine of that angle will be smaller. The sine, you know, if you draw a graph of the sine function, what does it look like? It looks like this, where that point is 90 degrees, and this is 180 degrees and 270 degrees. And so what you've done with this picture here is you've gone beyond the point. You've gone over here where the angle is more than 90 degrees, and so the value of the sine, it reaches its maximum of 1 here, right at that point when it's 90 degrees. Here it's gone beyond that, and so it's less than 1. The sine of the angle is there. So it's answer choice A is the correct one. Okay, now 31. This problem might be a little bit tricky, but it's useful because it lets us illustrate the importance of a concept we've talked about before, which is center of mass. And so what the problem is, just to redraw it here, is you have this board, and I'm drawing the board with some thickness because you're supposed to think of the board as being massive. You're supposed to, and the idea that it has a significant mass, a mass that matters compared to the masses of other things in the problem. And then I have a weight hanging from the end of here, and this is 3 kilograms. So you know already, you can say immediately that this is 30 newtons of force going down this way. And then you say there's a distance here of 0.2 meters, so that's 1/5 of the length of this thing, because the total length is 1 meter, that's what you're told. So 1/5 of that length. You have a tension force going up this way. And you're told that this thing is in so you're assuming that it's in equilibrium. And you're asked how much, what's its mass? So what is the mass of the board? And so that's mass. Now, how could you possibly answer this question? I mean, you're not told what the tension is or anything. Well, what you should do is you should assume that instead of thinking about the board, you remember when I had the hammer, I told you how when the hammer rotates, you can think about the complicated motion of the entire hammer as motion about its center of mass, which is very close to the head. Well, here, you can think about the downward force. I'm going to cheat and extend my board a little longer just to make the picture look nicer. You can think about the downward force of gravity on the board. So I'll call this here MB as being exerted at its center of mass. So that's right here. And so this is going to be MB times G going downward. Now, where's the center of mass of the board? Well, the problem tells you the board has a uniform density, so that tells you it has to be right at the middle of the board. Now, if I start over here, so if I draw my coordinate system, if I went, this distance 0.2 over, the distance to the center, I drew that in a messy way. The distance to the very center here, of course, is 0.5 meters. And so the difference between those two distances here is 0.3 meters. Now, the tension is exerted upward like this. And so what you can do is you can say that the torque, so I can call this torque 1. That's the torque exerted by this mass here. And I can call this one here torque 2. That those torques have to be equal to each other. And now I should be able to solve the problem. So if I say torque 1 equals torque 2, well, now watch how this falls out. What was torque 1? Well, in both cases, the forces are straight down, so the signs of the angles are 1. So the torque 1 is just this force here, 30 newtons, times the lever arm, which in this case is 0.2 meters. So this is 30 times 0.2. And then what's going to be over here? Well, there's going to be a force which is going downward. Now, since I'm saying the force is downward, that lets me call G positive because the acceleration agrees with the direction of the force. So I'm going to have this force, which is the mass of the board. Now, that's what I want, times 10. That's the acceleration due to gravity, times the length of that lever arm, and that's 0.3. And I haven't put in, I mean, here I could put in newtons, here I could put in meters, etc., etc. I'm just simplifying things here. So this comes out to 6 on this side of the equation. What does this come out to? 10 times 0.3, so 3 times the mass of the board. I shouldn't write that like it's a multiplication. 3 times the mass of the board. So I divide both sides by 3 and I get the mass of the board is 2, and the units are going to be kilograms. And that's answer choice B. Now notice what crucial use that made of this idea of center of mass. You were able to think of the entire board as just being concentrated at that one point. If you hadn't thought of doing this by center of mass, I don't think you'd be able to solve the problem in any reasonable way. Whereas if you do that, it becomes a very simple equation and you get the answer quickly. Okay, so there's one more. And once again, I have failed to update my number here. That, of course, was number 31. So this now is number 32. This I don't think is such a difficult problem. It says there's a seesaw, and the seesaw is represented in this kind of rough schematic way. And you can go 5 meters in this direction, so that's 1, 2, 3, 4, 5, 3, 4, 5. This is the 0 point where it's balanced. 1, 2, 3, 4, 5 in that direction. And it says that a 40 kilogram student or kid or something or other that'd be pretty small actually for a student. I have a 43 kilogram student, I think, but well, maybe she's gained weight. But anyway, so you have a 40 kilogram student that's pulling down here, and so you know that that force going down that way is 400 newtons. And so you want to balance over here. You want to put a 50 kilogram student, and you want to put somewhere on this side of the seesaw. It's funny, you've probably been laughing for the last 3 seconds because I multiplied wrong. 40 kilograms times 5 meters is 200 newtons. Well, no, that's not wrong. I'm outsmarting myself. I'm thinking about torque. Okay, so this is correct. This is the force due to gravity. See, I'm getting myself confused here. This is mg. So if 40 equals m, so m in this case m of I'll say this m1. This is the first student over here is 40 kilograms, and then so the force one, at this point is 400 newtons, and so the torque. Now the torque one, this is going to be 400 newtons times the length of the lever arm, which in that case is 5, and so this is 2,000. Now over here, what I'm wanting to solve for is the length. So I can call this R, because that's, from my torque equation, my general torque equation. I'm going to have torque 2 is equal to F times R. Since the student's sitting on it, the force is going straight down, and so the sine theta, there is a sine theta here, but it's 1, and so we forget about that. It's FR. Now, because there's 50 kilograms here, we know that force is 500 newtons. And so this says that this is 500 times R. R is what we're solving for. But we know that it has to balance this one for the thing to be balanced. So what do we end up with? We end up with 2,000 equals 500 R. And so R is 4. Now you probably knew that just by, say, put the 40 at the 5 and the 50 at the 4 and they balance. And if so, well, good for you. That's the best way to save yourself time on these MCAT problems. In any case, it comes out to answer choice C, and this completes the first set of problems.